I just say hello, everybody, and thanks again, all the participants again. And we can start. We already have a quite large number of participants. So I ask Alessandra to introduce the colloquium of today, and thanks also the organizers for that.
Thank you very much, Stefania. So it's a great pleasure to have today here Cumrun Vafa from Harvard University, who is really the case here, needs no introduction or very little introduction, because his contributions to theoretical physics are renowned. In particular, in the field of string theory, he gave enormous contributions that always walk a very interesting line between the more mathematical and geometrical aspects, but also the very deep physical implications of the field. In particular, his work on symmetries in string theory and on F theory has been of very deep impact to the whole field. More recently, a major contribution of Cumrun, which will be the topic of today's colloquium, was the study of the conditions on the vacua of string theory that may or may not allow for a vacuum to be considered physical and therefore to make contact with the real world. So this will be the topic of today's talk. And because of that, I don't want to say much more on this, and I think it's just best if I leave the microphone, so to say, to the speaker. So please take it away. It's a great pleasure to have you here.
Thank you so much, Alessandro, for this super kind introduction. It's a great pleasure giving a talk here. I have not had the pleasure of visiting the Galilei Institute yet, but I cannot wait till the COVID is over and I'll visit it. So here, given what we have, the situation we are in, I'll be doing this virtual one, of course, and let me share my screen. So I'm assuming that you now can see my screen. Is that the case?
Yeah, that works.
Great, and so I can start my presentation. So I'm going to talk about string landscape and the swampland. The idea of quantum field theories has been studied for a long time by now, and without gravity, if you don't include gravity in the mix, I would say they are relatively well understood, and they beautifully describe the interaction of all elementary particles we know, captured by beautiful Feynman diagrams. And so we could say by now we kind of know what constitutes a consistent quantum field theory, as long as we don't include gravity in the mix. Now, to include gravity, that is Einstein's theory, and describe it in quantum theory, we need to couple what we call coupling the quantum field theory to gravity, which means we introduce space-time which is not necessarily fixed, but fluctuating. And so in other words, we promote the metric on the space-time as a dynamical field in the action, and we add the Einstein term, and coupling it with matter and the gauge fields and so forth, we have this mixture of an action, and we can then consider quantum field theory as integration over the fields, the matter fields, as well as the metric with the usual action principle. This approach does not work. The infinities appearing in the Feynman diagrams are incurable, and so a conventional approach to quantizing gravity does not work, as Feynman discovered the hard way in the 1960s. The most natural conclusion from this, theoretically, would have been, well, gravity cannot be coupled to quantum fields and should always be viewed only as a classical background. Of course, this is not acceptable because we know that we do have both quantum mechanics and dynamical gravity in our universe. So therefore, we have to find a better solution. String theory offers a solution to this problem by replacing strings, which lead to consistent quantum theories of gravity. Of course, this would entail replacing the Feynman diagram with these wordsheet diagrams where the strings are replaced, the word lines are replaced by word sheets and these tubes, and the joining and the this and joining and splitting of strings are naturally captured by this beautiful Riemann surface. And the resolution of the singularities that the particle theory had turns out to be related to the fact that the oscillation modes of the strings are crucial in resolving the inconsistencies associated with the Feynman diagram. So the fact that the string has a finite size turns out to be a key factor. But it's natural to ask, can we get every consistent quantum field theory in 4 dimensions coupled to gravity from string theory? Now, string theory comes with 6 extra dimensions, and these should be viewed as compact, tiny spaces, which have so far avoided detection. So there are many solutions to what these extra compact dimensions can look like. This is cartoons for them. So we think about the space as this, the 3 plus 1 dimensional space-time as these yellow grid I have denoted here, and the internal space as some kind of a compact geometry that typically is frozen and the same for all the points in the space-time, for the ground state at least. We can get objects from the different kinds of particles and forces and so on, depending on what are these excited states of strings, or these wrapped states could be different kind of particles that we get from the perspective of 3 plus 1 dimensional space-time. And so we can get a diversity of a huge number of possible would-be physical theories in 3 plus 1 dimensions. For example, one internal compactification might give us SU4 gauge theory with 2 generations and with certain interactions, and another kind of internal geometry might give you another gauge group, let's say SU3 times SU4, SU5 with certain matter. And then the question is, can you choose something on the left side? Can you choose some kind of a geometry on the left side, which give you an arbitrary consistent quantum field theory coupled to gravity? The surprising answer, perhaps, is that we cannot get arbitrary quantum field theories. Indeed, we seem to be obtaining only a finite number of quantum field theories from string theory. So, for example, suppose we talk about the theory with maximum amount of supersymmetry with matter in 4 dimensions. So if you take in 4 dimensions, the maximal supersymmetry, which includes gauge groups, is n equals to 4 supersymmetric theory. The rank of the gauge groups we get from string theory is always less than 23 for n equals to 4 supersymmetric theories coupled to supergravity. In particular, if you take the gauge group to be SUM with n bigger than 23, all of which are not only consistent quantum field theories, but among the most beautiful quantum field theories, because after all, n equal to 4 supersymmetric quantum field theories are finite, are nice theories in 4 dimensions, are among the most beautiful ones. But no matter how beautiful and finite they are, if their rank is bigger than 23, you cannot couple them consistently to quantum gravity. By this, I mean quantum gravity in 4 dimensions. You could potentially couple them quantum gravity in higher dimensions. For example, in string theory, if you have the 3 branes, you can couple them to 10-dimensional gravity, no problem. But you cannot have a dynamical gravity in 4 dimensions that would be consistent with gauge groups which are bigger than rank 23. So the quantum field theories from string theory form a measure 0 of consistent quantum field theories. You see, for example, in this example, all the M's are perfectly fine quantum field theories, but gravity says there are only a finite number of them, namely the ones with M less than 23, that can arise as consistent theory of quantum gravity coupled to matter. And so a generic consistent quantum field theory cannot be consistently coupled to gravity. And this was the lesson that Feynman had already learned the hard way in 1960s, that things are not working right. And so the answer is yes, generally they won't work right. And there are only a few gens, very, very limited possibilities that can possibly arise in a consistent way. And in some sense, they seem to be finite, as I will try to explain. And here is illustrated by the simple gauge group, 4 dimensions with maximal supersymmetry. So this raises 2 questions. Does the fact that most quantum field theories do not arise in string theory a deficiency of string theory, or a general conclusion about consistency requirements of coupling for coupling to quantum gravity? In other words, is it a problem for us, namely string theorists, or no, it's a more general feature of quantum field theory coupled to quantum gravity. Now, evidence is emerging that this is not a deficiency of string theory, but subtle reasons for consistency of quantum gravity. And how do we get these subtle reasons for consistency? Many of them get connected to basic facts about any quantum system. For example, unitarity, and in the context of quantum gravity, consistency of black hole, unitarity, and entropy properties of black holes. So different facts about quantum gravity, like black holes, come to reinforce the perspective that many, in fact, almost all quantum field theories are inconsistent when you try to couple them to quantum gravity. So what are the criteria that distinguish a good quantum field theory, what we call part of the string landscape or quantum gravity landscape, from bad ones, or what we call the swampland? So quantum field theories which belong to the swampland. This is part of what's called the swampland program. So we want to know, so if you think about this as the space of all quantum field theories which are consistent, there are only a few of them which kind of arise from consistent theories of quantum gravity, and we want to know what are these good ones that do arise. So you can think about the space of all quantum field theories like this green space, which generally they don't work when you couple to gravity, and we call them part of swampland, except very few of them, in fact, finite number of them, which can possibly seem to arise in the context of consistent theory of quantum gravity. And of course, hopefully our universe standard model is one of them. So, of course, since this space is infinite, the space of consistent quantum field theory is infinite, to try to pick which points are good ones, landscape ones, is like finding a needle in the haystack. So it's going to be very difficult, and that's not going to be possible. So what we're going to do is actually find the things to rule out, like saying that if you're on the right-hand side of the space, you're in the swampland, or if you're on the left-hand of space, you're in the swampland. So to rule out theories as not being consistent with quantum gravity is far easier than to say, oh, this exact theory is a particular theory that does exist. So we want to kind of come up with requirements that would distinguish landscape from the swampland. So there has been a number of proposed requirements for a consistent theory to be part of the landscape, for a consistent effective infrared theory to be couplable to quantum gravity. Here I have stated about 7 of them. And these is by no means the only set of conditions people have come up with, and the list is growing every day, and so people have various extensions and ideas that are continuing to be developed at a rapid rate. And here I'm going to illustrate these ideas through the perspective of these 7 conditions. And needless to say, this is not just my work, it's the work of many people, and I'm not going to distinguish who has done what. So please bear in mind that I'm just going to view this as the review of the work that the whole community is doing on this subject. So the first one we're going to talk about as the requirements for a consistent theory to be in the landscape is that there are no global symmetries in the quantum theory of gravity. That is, the only symmetries that are there are gauge symmetries, local symmetries, no global symmetries. The next one is uniqueness of quantum gravity. That this is what's called the cobordism conjecture. It's related to the fact that any 2 consistent theories of quantum gravity are connected by finite action processes to one another. All gauge charges appear in the spectrum. So you have gauge symmetries, and not only you have gauge symmetries, but if you have a gauge symmetry, you should have all possible charges which are allowed in the spectrum in your Hilbert space. Scalar fields typically have infinite range in quantum fields, but in string theory, in a sense, they are finite range. And more effectively, what this means is you in a distance in scalar field webs, you go to a dual description of the theory, which is called the duality conjecture. That you get a dual description of a theory emerging at infinite distance. The next one is that the theory, any consistent theory of quantum gravity admits light or this light could be light or not, but in general, higher dimensional objects, like in string theory. Gravity is always the weakest force, as it is in our universe, and this is called the weak gravity conjecture. And finally, there are restrictions on critical points of positive potentials. Whenever you get positive potentials in quantum gravity, there are severe restrictions on their structure, it seems. And specifically, if you look for minima or critical points, and this will have some cosmological implications, and these are related to de Sitter conjectures. So to start with these ideas, I want to first review some very obvious, some kind of very long-known, well-known facts about black holes. So if you fix, I just remind you that if you fix a charge Q and a mass M, then as long as the mass in Planck units is bigger than the charge, there is a black hole. There's a solution to Einstein's equations. And the extreme case where M is equal to Q can also occur. This is called the extremal black hole. Moreover, black holes have thermodynamical properties, as we know from the work of Bekenstein and Hawking. And in particular, they carry an entropy. And the entropy of a black hole is given by the area of the horizon divided by 4, measured in Planck units. So these are some basic facts that we kind of know about quantum gravity. We expect this to be true in any quantum theory of gravity, so we can kind of use these facts as guiding principles. So let me come one by one to discuss various criteria we have talked about consistency of quantum gravity theories and requirements for it. The first one was the fact that there are no global symmetries in quantum theory of gravity, and the idea is rather straightforward to show that there cannot be a global symmetry. You consider a global charge Q, and you throw a conserved charge inside the black hole, and it goes inside the black hole. And once it's inside, there's no remnant, or there's no impact of this outside the black hole, because this has no electric charge or no magnetic charge coming out, because it's a global charge. And so, as far as the outside is concerned, because of the no-hair theorem for the black hole, you don't see any charge. You just see the mass or the spin and so on, but no global charge. But we know, according to Hawking, that this will evaporate. And once you evaporate, since there is no preference between different signs of the charge, you emit the charges plus or minus equal amount. And therefore, during the process of evaporation, there's no charge violation. But you started with some charge originally, and there's no charge at the end. So therefore, you lost the original charge. So therefore, we just learned that the charge is not conserved. So this idea was a relatively simple idea that shows the fact that global symmetries are not possible in a quantum theory of gravity. This is also, of course, the case in string theory, as we have seen, but the idea is more general, as you can see. The next one is uniqueness of quantum gravity. A generalization of no global symmetries conjecture is this, basically. So any consistent quantum gravity can be deformed to any other through finite action physical process. In the context of string landscape, this means that any compactification of string theory can be deformed to any other one. So suppose you have a compactification of string theory on some manifold M, and suppose this gives you some quantum gravity that we observe, let's say in 4 dimensions, and somebody else says, no, I don't want that manifold, I choose a different one, N, and this gives you a different quantum gravity in 4 dimensions. The statement is that there's a finite action process, no matter what M and N you choose, and no matter what kind of fluxes or branes and so on you put in them, there's a finite action process which takes you from one to the other. In other words, there's no way you can restrict that. You can say that these M and N are totally different universes that can no way be connected to one another. This is a kind of a property of what we call the uniqueness of quantum gravity, that there's always a way to go from one to the other. So the configuration space is connected. This third criteria is that all charges are in the spectrum. Suppose we have a U1 gate symmetry. All integral charges to exist, but the question is, are there such states in the theory for all charges? Without gravity, a priori no reason for this to be true. For example, we can consider a pure U1 Maxwell theory coupled to gravity with no charge states at all. However, it turns out this is not consistent. And if you include gravity, this does not make sense. So let's explain why. Consider, as we mentioned, there's a black hole for masses and charge. As long as the mass is bigger than charge, there are such black holes with some event horizon. And the number of states, because the area over 4 is the entropy of the black hole, the number of states goes like e to the power of a over 4. So that means there's a huge number of states with a given mass and a charge, as long as this is a big macroscopic black hole that you can trust this classical picture or semi-classical picture. But if this is big, you might say, well, it doesn't necessarily have to have a fundamental charge. It's a big charge. But what we can do is take a big charge and take a big charge plus 1 and add another one black hole with the charge minus q and combine them together, and you get the charge 1. So you can get any charge you wish by combining or colliding black holes together, which are consistent. So you generate every charge in the U1 through these black holes. So therefore, all charges should be in the spectrum. The next criteria is that the range for the scalar fields is finite. This is related to what is called the duality conjecture or the distance conjecture. Consider a scalar field phi, and without gravity, we usually have no restriction on its range. For example, we take phi to be ranging from minus infinity to plus infinity. However, with gravity, it seems that the range for the field is effectively finite. What does that mean is the following. Suppose you start with an effective description of the theory with a certain number of particles with certain masses. That effective description is valid only for webs of this field in a finite range of order 1 in Planck units. If you increase the range of that scalar field beyond order 1 in Planck units, what happens is that the effective theory description breaks down. And the way it breaks down is that you end up getting light states that was not part of your effective theory originally. And the farther out you go in the field space, the more and more lighter states you get. And these lighter states turn out to be describing the dual phase of that particular string. So this is related to the duality conjecture. So suppose, for example, your field space, instead of one scalar field, you have many scalar fields. In your action, you have some kind of effective term like GIJ grad phi squared term. So this GIJ term allows you to define a metric on the field space phi, on the web of the field space phi. And the statement is that if you vary by order 1 in M Planck, you're fine. But if you go too far, much more than order 1, you could still go. But what you find is that you're approaching certain limiting corners where a dual description comes up here in these corners. And you get the tower of light modes emerging for these large distances in field space. And the masses of these towers goes exponentially down with distance. In the form, the mass goes like constant times e to the minus alpha phi, where alpha is order 1 in Planck units. So this is quite remarkable that there's a priori no reason why this should be the case, but this is what we see in string theory. And so this is one of the basic facts of quantum gravity. There's no simple explanation of this fact that we know of yet. And this is one of the amazing features of string theory, and we still don't have a deep understanding of why we end up getting string dualities. A potential application of the distance conjecture would be something like this. So you take, for example, the cosmological constant. The cosmological constant can be viewed as a distance in field space because, as we said, the quantum gravity, in quantum gravity, the fact that you can go from any vacuum to any other one, in particular, suggests that the cosmological constant itself should be viewed as a web of some field. And it's natural to parameterize this in an exponential way by using the distance on field space. And so this suggests that as you go in large distance in phi, the web of the cosmological constant going down, for example, for the web that corresponds to the cosmological constant that has been observed, 100, and therefore you expect that you're getting the tower of light states in some form. And so we are getting some kind of the light tower in the form of e to the minus alpha phi, which means that we should get particles with masses which scale like lambda to power of order 1 in Planck units. So m should go like lambda to the a, where a is order 1. And this is not too unlike what we see in our universe. For example, the mass of the neutrino is lambda to the 1/4, and you have similar powers for different particles spectrum that we have. So this suggests that this hierarchical structure of masses that we see in the standard model might not be unrelated to why the dark energy is so small. So these get to relate facts about particle physics and facts about dark energy, which are a priori completely unrelated facts. Another feature is that in any quantum theory of gravity, we do have extended objects. There must be extended objects like in M theory, we have membranes, or in string theory, we have strings. Now, this also, at least heuristically, follows from the previous criteria that at infinite distance, you get light states. And to see this, start with your theory of gravity in some dimensions and compactify it on a circle. So you take a periodic circle, you put your fields on a circle, and you go to a lower dimensional theory, one lower dimensional theory. In this way, the radius of that circle appears as a web of a scalar field with a kinetic term of the form 1/2 grad phi squared. So as far as this lower dimensional theory, you have one extra scalar field. And now we can apply our criteria 4. The criteria 4 had told us that you have a distance, you get the light states, which go exponentially with phi. So let's apply this to this phi here, where phi is the radius related to the radius of the circle. So if you take phi to be large, the radius is becoming large. And so what is the tower of light states? Well, the tower of light states are just the momentum modes around the circle with a large radius circle. Their energy goes like 1/r, their mass goes like 1/r. And indeed, that's the case. It goes exponentially with phi because r is e to the phi and therefore goes like e to the minus phi. So this is the example that I was mentioning, that the tower of states go exponentially with distance, just like the KK modes are an example of this. However, there's something else we can do. We can go to phi goes to minus infinity. If you go to phi goes to minus infinity, that corresponds to radius going to 0. But that's also at infinite distance in field space. So at infinite distance in field space, that corresponds to r equal to 0. So therefore, the duality conjecture or the distance conjecture will tell you that there should be some things becoming light. But there is nothing becoming light if it was a quantum field theory coupled to gravity. The usual quantum field theory of particles, as you take the circle to go to 0 size, freezes all the momentum modes around the circle because they become infinitely massive. And so you basically get what's called a dimensional reduction. You just take that same theory and ignore one direction, and you write in lower dimensional theory, and there are no light states. So therefore, particle theory fails this test. So it won't give you it won't work. How can you get a tower of light states? Well, the only way we know of is that if it kind of feels the global geometry of the space becoming light, and how that happens is that the only natural mechanism for this is if we have extended objects like strings or membranes, which can feel the size of the space, can wrap around that extra direction of the space, so that when the string shrinks, space shrinks to 0 size, you can basically get a light particle or light state in lower dimensions. So having an extended object which feels the global topology of the space is necessary for it to end up giving a light state. I see somebody's asking questions. Yes. I think Jan is asking a question. Please.
Yeah, maybe can unmute. Yeah.
Yes, actually, I wanted to ask about this uniqueness of quantum gravity.
Yes.
So I'm given to understand that this uniqueness of quantum gravity comes from the fact that we are compactifying string theory in various cases, and then these various cases are related by the by this Duality conjecture, right?
Yes.
But this does not apply to the uniqueness of quantum gravity in general, because we have different approaches to quantum gravity, such as loop quantum gravity. And this is not what you are trying to say.
Correct. So bear in mind that these statements that I'm making about the Swampland are not proved. So I'm not claiming that I have a proof of these statements. Even in string theory, we don't have a proof that you can go from every m to every other n. So it's not a proof. However, we have evidences which point in that direction. And these will get related to these relations for swampland conditions reinforce each other. For example, the fact that there are no global charges is consistent with the fact that for every class M, you could go to any other class N. Because if you could not, you could define a notion of a charge which prevents you from going from one to the other. Now, I told you that there's no global charge. So the fact that there's no global charge reinforces the idea that indeed it's not possible. It should be possible to go from every one to every other one. It doesn't prove it. It doesn't prove it, but it's kind of consistent. And it turns out that this idea explains many facts in string theory, like existence of various kinds of singularities that we may not have thought existed and so forth. All of them are consistent with this cobordism conjecture or this uniqueness of quantum gravity. So bear in mind that the conditions I'm spelling out are the things we have learned from string theory, many of which can be explained by facts beyond string theory, but not all of them. And moreover, these conditions reinforce each other. So they form a coherent set, which is why we believe they have a validity beyond string theory. Okay.
So I think there were a couple more questions in the chat. If you don't mind taking them now. Or
sure. Anytime, whatever your format of your talk is, I don't mind either way. Whatever you usually do.
I think we can take them now. Maybe it's more interactive that way.
Sure. So I don't see the chat.
So let's see. I'm trying to unmute the people who asked this question so they can. Or maybe the GGI staff can help me in unmuting Ivano and Jose. Let's see.
Maybe I ask my question first.
Yes.
Yeah.
I just wanted to know, when you say no global symmetries, you mean just exact ones, meaning
Correct.
Global symmetries such as lepton number, for example, could be broken by gravitational instanton effects in an explicit manner.
Approximate symmetries, I have no problem. I'm talking about the exact symmetries.
Okay, thank you.
And I think that there was another question by Ivano.
Yeah. Hi. So I was wondering, what do you think about the validity of the generalized Swampland distance conjecture, namely the one in which one takes into account the variation of non-scalar fields, such as the metric, for instance?
Yes, I think it seems like we have evidence for the generalized version. Yes. So there's more general than just scalar fields. Yeah. So, here, bear in mind that here, I just want to review the basic ones. There are many ramifications of each one of these conditions and much more detail that I'm providing. So I apologize for not being comprehensive and giving all the nuances that each one of these conditions have and what evidences we have and so on. So I'm just trying to give you a flavor. I'm assuming that most of the audience is not expert in this area, so I'm kind of aiming it at the people who are not familiar with this whole program at all.
Right, thanks.
For the expert.
No, I was just asking mostly because from what I gathered from the literature, the somehow the status of the generalized version is somewhat, I don't know, cryptic, let's say.
Well, there are various generalizations that one can talk about, and we can discuss the various aspects of them. So there's the vanilla version, and then there's these ramifications, and people have taken it to different things. Some of them may or may not be as trustable. So I'm not saying everything that people suggest necessarily is correct. But at any rate, for the version I said, we have a lot of evidence for the one I mentioned.
Can I ask a question?
Thank you.
Yes.
Yes. So do you distinguish between consistent quantum gravity and something that comes from string theory?
No, not in principle. I mean, in principle, there could be a distinction. So I'm allowing for that to be the case. I think we should keep an open mind for that. That's the whole point. If we can, the question is that can we understand the principles that we have learned from within string theory in a broader way, so that we can see what, if any, is missing in terms of the things that string theory doesn't give us, or is it identical to what we get from string theory? So that's what we're trying to aim at. So if from string theory cannot be connected to a deep principle of physics like unitarity and this and that, then we can be doubtful about it. So we have to kind of bring it all the way to basic principles. So that's the whole. Right now, I cannot say for all of these conditions I'm giving you, we do have a deep principle. But for many of them, as I try to explain, we have connections with basic facts of, for example, black holes and consistency of unitarity of the black hole evaporations and different facts like that, together with the fact that they fit together, these conditions, and arise in string theory. So it's a kind of a mixture of connections with basic fundamental principles of physics and observations from within string theory right now.
Thank you.
So I see no other questions. So I think
Okay, so I will continue.
let's carry on.
So the next criteria is what's called the weak gravity conjecture, or that gravity is the weakest force. So in string compactification, it has been observed that whenever we have charged particles, the electric force between the elementary charges are stronger than the gravitational attraction. So if you have, say, 2 electrons, the gravitational attraction is much, much smaller than the electric repulsion. And so we say that mass of the electron in Planck units is much smaller than its electric charge. Well, this is observed in our universe, of course, because as you see, the mass of the electron in Planck units is like 10 to the minus 23, and its electric charge is 10 to the minus 1. So indeed, 10 to the minus 23 is much, much less than 10 to the minus 1. So this is true in our universe. But the statement is that in any consistent theory of gravity, this seems to be the case, that whenever you have a U1 electric charge state, you have whenever you have a U1 gauge theory in a gravity theory, you always have electrically charged state whose mass is not too big in Planck units in comparison to the charge. So why is that? In other words, we could have naively thought that, well, why not? Could have been that the electron mass is, I don't know, 100 times the Planck units or 10,000 times the Planck units, or much, much bigger. Why not? Why should it be that the electric charge is always less than, the mass should be less than the electric charge? So there's a kind of an explanation of this phenomenon, again, using black holes. So consider a black hole, so consider a big black hole, and I told you that for mass equals to charge, there are these extremal black holes. So typically the mass is bigger than or equal to charge, but mass equal to charge is the limiting case. Now, we know that the black hole evaporates, and so what happens if you emit a tiny electric charge state with mass and small m and small q? I'm using small m and small q to denote small mass and small charge, and capital Q and capital M to denote the big mass and big charge of the black hole. So when you emit a charge of small charge m and q, mass m and charge q, the original one, the charge goes down to q minus small q and the m to m minus m. But originally we started with q equals to m. However, at the end, when we go to this one, the black hole should still be consistent with the condition that the total mass is bigger than or equal to total charge. That was one of the consistency conditions for the black hole. And therefore, this tells you that an opposite thing holds for the little mass and little charge. So the m should be less than or equal to q. So in other words, the elementary excitations that you're evaporating from the black hole better be mass less than or equal to charge, if the black hole is to evaporate. So the idea that there are these charges consistently fits with the fact that the black hole should be able to evaporate. And that is one of the motivations for this weak gravity conjecture, that there are always charged states whose mass is less than charge. There is a limiting case where mass equals to charge for these elementary excitations, and this occurs in supersymmetric states, and these are called what's called the BPS states. Now, there's further evidence for the weak gravity conjecture. So take pure Maxwell theory, coupled to Einstein gravity. It turns out that this leads to naked singularities for certain examples. Naked singularities are singularities that are not hidden behind the event horizon. And the way this arises in Maxwell theory coupled to gravity turns out to involve regions of strong electric field. So this has been observed by groups in the past few years, and so it turns out that the weak gravity conjecture leads to avoiding this phenomenon. Of course, a priori, One could have thought there's nothing wrong with this, but it turns out that there's this condition called the cosmic censorship that suggests that naked singularities should not appear in the quantum gravity. And so it's interesting that weak gravity conjecture does get rid of this phenomenon. So let me explain how that works. So first of all, if we have a U1 theory, it cannot be pure Maxwell theory, because as I explained, there must be charged spectrum based on the condition for black hole entropy. So there must be charged states. That's the first statement. Secondly, the weak gravity conjecture says that these states, these charged states, cannot be too heavy, that at least some of them, there's some of these states whose mass is less than charge. So what happens when the electrical field becomes strong is that since their mass is not too much compared to its charge, the big electrical field creates these masses, creates these particles from vacuum, these charged particles, and these charged particles get to screen the electrical field, and they avoid the naked singularity precisely at the right moment that the naked singularity was about to form. So it's actually a sharp statement. So you can kind of derive this mass less than or equal to Q condition by the requirement that the naked singularities do not appear. So it's an extra condition that you can kind of see from pure gravity reasoning, lending further support to this weak gravity conjecture if you believe that there should be no naked singularity. So you see this is how, Domenico, how we said that we can kind of begin to believe that these are beyond string theory. This was not a motivation. Avoiding naked singularities was not a motivation for weak gravity conjecture, but this is the application it's found. And the application, of course, the naked singularity was not proven to be a condition for good quantum gravity, but kind of fits together. So these kind of ideas reinforce one another. Another application of weak gravity conjecture to our universe is the following. I find this application actually quite beautiful. Consider de Sitter space. So we know that we live in our universe, we have a dark energy, which is positive. And so we know it's almost constant. We don't know it's exactly constant, whether it could vary or not, but at least it's quasi-constant. So roughly speaking, we should be living in approximately a de Sitter space now. You can consider now evaporation of black holes in de Sitter space, our universe. Well, if you take small black holes, not huge black holes, then you get the same condition I told you about weak gravity conjecture. And this gives you the condition that the mass is less than a charge for the evaporation of the small black holes. But you could also consider large black holes which are as big as the Hubble horizon in our universe. And you can take them to be charged, and you find that the condition that their evaporation is consistently done, that you won't get a problem with singularities of the black holes, leads to the condition that there's a lower bound on the mass, not an upper bound. In this case, the mass would be bigger than the charge to the 1/2 times the cosmological constant to the 1/4. This is interesting because it gives you actually a prediction on both sides of the lower and upper bound for the mass of the light elementary charge states in our theory, in our universe. So for example, for our universe, there's a U1 electric charge, and therefore the lightest particle, which we know is electron in our case, should have a mass between Q and Q to the 1/2 times lambda to the 1/4, which tells you that the mass of the electron in our universe should be between 10 to the -1 and 10 to the -31. The mass of the electron is about 10 to the -23. Okay, so you may not find this an impressive prediction, but still it's a prediction of these ideas that you see, especially if you look at the exponents, 23 between 1 and 31 is not such a bad kind of ballpark estimation for these numbers in the sense of the log sense. At any rate, so people who say that string theory makes no predictions, well, this is one of them at least. You could say that this is one very concrete prediction that comes from string theory ideas, which has no reason a priori to be true. So these kind of ideas are beginning to kind of be related to the facts we observe in our universe. Interestingly enough, this lower bound is related to the mass of the neutrino, which is about this scale. And it'd be interesting to try to see if one can explain why the mass of the neutrino roughly. Unfortunately, the neutrino has no electric charge, so therefore this cannot be strictly applied to neutrino, but it's kind of tantalizing that we can possibly have a gravitational explanation of the lowest mass we have in our universe, lowest non-zero mass being neutrinos. So for the last general topic condition I want to talk about is the restrictions that we get from quantum gravity on critical points of potentials which are positive, and how flat potential can possibly get. So this is an important question for early cosmology, and for example, in the context of inflation, or late cosmology, in the context of our universe today, in particular the dark energy. For example, in the context of inflation, we consider potentials like the one we have drawn here, where the original potential is relatively flat over a wide region and with positive potential, and then it falls down to some minimum, and perhaps that's the minimum we are in today, where the minimum value of the potential denotes the dark energy that we have, lambda. So both the critical point here as well as the flatness and the extended to what extent it's flat is important for questions of cosmology in particular. So, okay, so what does string theory have to say about these kind of potentials? Actually, this is extremely difficult for string theory to say something very definitive. And the reason is that supersymmetry must be broken. Whenever you have positive potentials, you have basically broken supersymmetry. And a lot of it is not a problem in general to break supersymmetry in string theory, no problem. You can consider background in string theory where supersymmetry is broken. But what happens when this supersymmetry gets broken, typically, we lose analytic control for most of the parameter space. So we can only have control of the parameter space in extreme weak couplings. But as soon as you want to have strong coupling statements, you lose total control. So supersymmetry breaking is a difficult thing. And so for the situation where the V is positive, we don't have too many things we can say in general. So what can we say? Well, the potential is a function of some field space, and this is the field space I was telling you about. There's some scalar field space, and there's some geometry for this field space, a metric on it. As I told you, as you go to extreme distances in the field space, you get a dual description where you get a weak coupling description. So at these extreme corners in the field space, we can describe situations like supersymmetry breaking in a semi-quantitative fashion. And people have studied examples of breaking of supersymmetry at weak couplings at these corners. And what we find in these corners is that the potential typically goes exponentially down. So in particular, for positive potential, you get exponentially going down potentials, like V goes like e to the minus some constant times phi. And the constants that we get seem to be bounded. It cannot be too small. Constant here, V prime over V, turns out to be always bigger than square root of 2/3 in all the known string compactifications. So therefore, not only you cannot make the potential flat at the end, you will always have a sufficiently sharp gradient relative to the value of the potential as you approach these infinite distance limits. So this is known in all the examples we know of in string theory. Okay, so what can we have? So, well, this is the story at the boundaries where we have analytic control. Inside this space, there's no perturbative description and supersymmetry is broken. We don't have much analytic techniques today. So we don't really know what's happening in the middle. Now, for example, you might imagine that the potential goes somewhere in the middle, becomes a minimum, and you get a, let's say, a de Sitter space here. But already we make a prediction that even if we have a situation like this, it cannot be stable because the potential is going down to 0 at infinity. Therefore, at best, it is metastable. In other words, if you are in this minimum, you will still decay away because far away you will have potential even lower. So no model of dark energy is stable. So this makes a prediction that our universe is not going to be stable. That's one of the predictions. So that is one of the predictions. Of course, we do not have a reliable evidence yet whether the de Sitter state, de Sitter exists in string theory. There has been putative attempts and constructions, but there's still being debated whether or not they're actual solutions. So we're not really sure about whether this actually is the case or not. So as I said, we know that far away, the slope v prime is bigger than a constant times v. And this fits nicely with the idea that as you go far in distance space, you get a tower of states whose mass goes like e to the minus some constant times phi. So since the potential typically goes like some power of mass, so if you think about that this tower of mass scales are affecting the generation of the potential, you might imagine that v also goes like m to the fourth with some power. Therefore, this gives you a potential which is exponentially going down, consistent with this pattern I told you about. So this fits together beautifully with this distance conjecture we talked about before. So what goes on inside? So in other words, what is the story inside this module, this hard place that we don't know analytically what's going on? And there are three possibilities. One possibility is that there are no restrictions, that there's no problem. You can get anything you want in the middle. This is unnatural, given that we have very specific boundary behavior for V leading to instabilities. So it cannot be totally arbitrary, given that we have some interesting boundary conditions. So this is a possibility that is possible, but sounds a bit strange. Another possibility is that what's called the de Sitter-Swampland conjecture is that either the same condition holds, that is, the slope is bigger than the constant times V, or if it's not, it should be sufficiently unstable. That is, you could have a situation where you're on the top of a potential. So the second derivative should be sufficiently negative, so it's not stable. In other words, this conjecture says that there is no metastable de Sitter. Everything is unstable. Either it flows away or it kind of rolls down the top of a hill. And then there's a third version of it, which is called the Transplanckian censorship conjecture. The Transplanckian censorship conjecture is motivated by the following conjecture, that if you consider a sub-Planckian mode and consider these sub-Planckian modes in a universe which is evolving exponentially or in whatever form, the final radius of that universe to the initial radius magnifies the Planck length by some amount, and that magnification of these Planck modes or sub-Planckian modes should not be bigger than the horizon that you end up getting. So in other words, the sub-Planckian modes cannot get bigger than the whole universe that is observable, because if it did, it would freeze out in the super horizon limit, and this would sound strange. Of course, again, this conjecture is not provable. This is just a condition that seems to be some kind of a motivation from saying sub-Planckian modes are not physical, but it's not necessarily provable. What is interesting is that if you use condition 3, you can prove that V prime over V at infinite distance in field space is bigger than square root of 2/3, which is what has been observed in string theory constructions. So in other words, this square root of 2/3 that I told you was observed in string compactification can be derived if you assume this conjecture 3, the Transplanckian censorship conjecture. So one might ask, what is the relation between Swampland conjectures and inflation? Well, inflation is not ruled out, but typical scenarios seem at least highly fine-tuned. So the duality conjecture leads to the prediction that we cannot have too large a flat region in field space because you get a light state, and so we should typically get a tower of light states that interferes with inflation. So getting a large region for the inflation is difficult. Not all the inflation models that require having a large distance in field space, but at least a garden variety of them do. Another issue is the slope conjecture, that with the same one, because we typically have, if you have these plateau models, it's not only a large distance is flat, the slope should be much less than like 0.02. C should be less than 0.02, which is order 1, but not that small. And then you can ask, okay, what if you assume instead of the de Sitter-Swampland conjecture, the Transplanckian conjecture? The Transplanckian censorship conjecture does allow metastable de Sitter, but it has difficulties with inflation because it will give you a very low scale inflation, 10 to the 9 GeV or less. And this is consistent with the epsilon and R, which is very, very small. And these end up being a very fine-tuned initial conditions for inflation, which seems very, very unnatural. So if Transplanckian censorship is correct, inflation models are I would say, ruled out or very, very unnatural. Now, you might ask, if it's unnatural, then what replaces inflation? Well, it turns out that the puzzles of early universe, in one form or another, hint at, is at odds with what we have learned in string theory, and this is dualities. You see, early universe is an extreme condition. If you just extrapolate backwards the FLRW, you find that the beginning of a universe, the radius goes to 0, and temperature goes to infinity. Well, these are extreme limits in string theory. And as I was telling you about, when radius goes to 0, you do expect to get Tower of Light states. As temperature goes to infinity, you can think about the temperature as dual to a radius in Euclidean space. Temperature going to infinity is the inverse radius going to opposite, going to 0. Again, you expect some light tower of states. So therefore, you expect that the original description of the theory breaks down. So very much we expect that what should happen based on string dualities is that the early phase of the universe is not described by the same effective theory we're familiar with, not the theory that we have today with 1 or 2 extra fields. It should have an infinite tower of light states emerging, which gives you a totally new description, a dual description of the theory in the early universe. So our universe would have emerged from a dual description, which is very unlike our universe. And so people have talked about various examples of this, and we talked about some aspect of this in the context of what is called the topological scenario for early universe. But I will not mention that here too much. So what do these theories predict about the present and the future? Well, if we assume that the Swampland conjecture is true, we can only be in a rolling potential situation like in quintessence. And since if you roll for a long time, you again get the Tower of Light states. So that says that after a while, you should get this tower, a kind of a phase transition. And you find by matching with the current observations that this should be no more than 30 times the Hubble time. So we should expect a phase transition of the order of 30 times the Hubble time if the Swampland conjecture is correct. If the Transplantian censorship conjecture is correct, we can use similar ideas to find that the upper bound for the lifetime is of the order of 2 trillion years. Basically 1 over root lambda times log of 1 over root lambda. This is not, of course, too far from what our current time scale is. Our time scale today is very close to 1 over root lambda. So thanks to this log, we have like a factor of 100 or so enhancement of the would-be allowed lifetime. In fact, either of these, the Sitter conjecture explains one version of the coincidence problem. This is a particular version of the coincidence problem. That's why the time scale associated to the measured value of dark energy, this is the time given by 1 over root lambda. Why is it so close to the current age of the universe? And the point is that the lifetime of the universe, from what I just showed you in using these conjectures, cannot be much longer than 1 over root lambda. And therefore, if any time the sizable fraction of the universe's energy budget is in the form of the dark energy, that time scale is the same time scale as the beginning of the end of that universe. In other words, whenever we measure the dark energy in a universe, we are basically have seen evidences or first indications of the demise of that same universe, according to these conjectures. So let me conclude by saying that Swampland conditions can lead to potentially observable consequences for our universe, for particle physics and cosmology. Almost all quantum field theories on the Swampland, and therefore fine-tuning such as hierarchy problems may end up having very different solutions. Hierarchy arises because you're assuming that the full set of quantum field theories are okay, and you look for why one of them is the one we live in. But if the actual set that you should be, what the prior should have been much smaller, and therefore within that prior, you might not have the hierarchy problem that we have today. These ideas suggest restrictions on light matter fields. Moreover, for example, the mass of electron as an example I mentioned, and it points towards restriction on positive energy in the context of quantum gravity. And I said why having positive energy should lead to local and global instabilities. And new ideas like dualities are expected to play a key role in the early universe. So thank you.
Well, thank you very much. Of course, it's always a bit hard to properly thank the speakers in these virtual seminars, but I think we are all very happy for this nice talk. And in fact, there have been already quite a few questions in the chat, so I would ask perhaps the GGI staff to help me out a little bit and start unmuting those who ask questions, so they can maybe ask the questions now during the discussion. So please, as soon as you are unmuted, you can go ahead. You should realize that you are requested to be unmuted, so you can just ask the question. So I think David can.
Yes, David.
Hello. Nice to see you. The Transplant conjecture is actually behind all the calculations of density perturbations generated at inflation, right?
Yes.
So do you think that these calculations are all irrelevant?
No, the calculations are correct. The calculations are correct. The calculations, if you assume the subplanckian modes, for example, as I said, the Transplant conjecture does not rule out inflation a priori, it makes it unnatural. So the idea is that the fact that
modes which are megaparsec today were Transplant definitely.
No. The point is that the modes that so they exited and came back. That's the point, right? So the modes. So if the mode gets so indeed the modes that would have exited our horizon would have been a problem. So for those classes of models, yes, that would have been a problem with the.
That's the general picture. That
yes,
every megaparsec mode was.
Yes. So those models would be
horizon and superplanckian. Okay, so you're agnostic about the origin of density perturbations, right?
Correct. So in these topological scenarios that we talked about in recent works with Agrawal and Gukov and Obeid, we talked about how you can get these fluctuations from a different perspective in these topological scenarios, where the early universe is coming from a dual phase, and our phase becomes a topological gravity phase. So the phase, in that context, the fluctuations arise due to the existence of the extra field, which has to do with which implements the scale anomalies in the context of the topological gravity theory. So the existence of these fluctuations are different in this context. The topological gravity scenario has some similarities to the inflation in terms of the steps that you have. So the basic idea, so let me explain that a bit more clearly. So in the context of inflation, what you do is that you take a part of your space and you blow it out. So you flatten things out, you kind of make things homogeneous and so forth. However, the way this happens in our universes, in these kind of string theory, is very different. What happens is the following. When you go to the early universe, the matter we are made of becomes very heavy. And we freeze out. What we are made of freezes out, including the space. So all the degrees of freedom which lived in our space will be frozen. And so therefore, our space becomes rigid and frozen, topological. So therefore, you could not distinguish structures within our space at the early universe. And that's a topological nature. You don't blow a space to become flat and homogeneous, but our modes freeze out. The dual space is where the action is taking place. So when you go from this dual phase and you come to our phase, then there will be a transfer of modes from those earlier modes to our modes when your universe becomes bigger. And that transfer of energy from that phase to our phase is somewhat like quote unquote reheating in the language of inflation. So steps that we have in this scenario is not unlike what one sees in inflation, but the motivation and distinction are different. In inflation, many of the things are trying to solve problems of why something is almost zero. Why is the curvature almost zero? Why is the horizon problem? Why is the things so homogeneous and all that? These problems get related to precisely to freezing out of our modes and the topological phase as being the early phase.
So is there a natural way to obtain flat power spectrum, nearly flat, almost flat power?
Yes. That's discussed in that paper. I can try to put it in the chat. If you get a chance, you can look at it. Let me try to see. This is the paper with Pratik Agrawal I mentioned, and Gukov, and my student Obeid.
Don't bother, I figure out.
By the way, let me take this opportunity to say that there is also a possibility for people to ask questions after the talk and to put some resources in the GGI page. so answers to questions or links to papers and so on, in order to keep the discussion open. But in the meantime, I think let's have David next, and then we will have Ivano and Kirill.
Yes,
and
I put it in
others.
the chat, by the way, both Domenico and I put the reference to that paper in the chat.
Yeah.
Yes.
So can I ask my question?
Please.
Thank you for this
Who's asking the question,
overarching
David?
view.
Brothers?
Yeah. Can you hear me?
Yes, yes, go ahead, please.
Thank you. You mentioned only one specific class of theories which was not obtainable, n equals 4 super Yang-Mills, which is much beloved of my colleagues in perturbative quantum field theory because of its attractive features. But they look at it in the tooth limit of the large number of colors where planar diagrams dominate, and we have a finite circle of convergence. So I think I heard you say that the tooth limit doesn't exist in your universe. Is that correct?
I'm sorry, David. I'm afraid that there is some problem with the connection of Cumrun. I don't see him. I think he might have disconnected just now, quite unfortunately. Maybe the GGI staff can see if anything went wrong.
No,
You also don't see him, right?
no, in fact.
Yeah, that's quite unfortunate, but I would ask maybe to wait a little bit online. Maybe there was some issue on his end, and then he will reconnect. And then I think David, you would have to ask again your question, because I'm afraid you might have missed it.
New message by him. Let me see. What is it?
So I don't know what happened to my internet.
Oh, here.
Okay, can I have a go at asking my question again? You mentioned n equals 4 super Yang-Mills, much beloved of perturbative quantum field theorists. I think I heard you say that the tooth limit, which is what people like very much, doesn't exist in your universe, because that's the large number of colors in the tooth limit, which gives the planar theory. And you're telling me that the number of colors can't be greater than 23. Is that correct?
So, half correct, half incorrect. So let me explain which part is correct. There's no problem, as I mentioned, with SUN for large and a tooth limit as a quantum field theory. You're asking it, you would ask a different question, whether you can couple that to gravity. Now, then again, there are two versions of that question. Do you couple it to 4D gravity or higher dimensional gravity? For example, in ADS-CFT context, we coupled it to 10D gravity, and there is no problem. The question is, can you take n equals to 4 Yang-Mills with SUN and couple it with n equals to 4 supergravity in 4 dimensions? The answer is no, if the rank is bigger than 23. Okay.
All right, then there was another question from Ivano.
Yes, hi again. So I was wondering, assuming the de Sitter conjecture holds, what would be, in your opinion, the most plausible alternatives for phenomenology? Maybe quintessence or some other scenarios?
Yes, quintessence is so there are two versions of this de Sitter conjecture. The one which is just saying that you cannot have a critical point which is stable, metastable, or the Transplant censorship conjecture. The first one, if it is the case, then the only alternative we have would be quintessence with sufficiently flat potential. That would be the only possibility that I can think of. The other one, for the other one, Transplantian one, allows you to have metastable de Sitter. But its lifetime of that de Sitter is not long compared to the Hubble time. Well, it's at most off by a factor of a log, but essentially it's the same as Hubble time up to a log correction. So in some sense, you do not have a very long-lived de Sitter regardless.
Yes, that's what I meant. Thank you.
You're welcome.
And then I think that Kirill also had a related question, maybe.
Yes. My question is an add-on to... Can you hear me?
Yes, I can hear.
My question is an add-on to Ivanus. I would like to ask whether... so if our universe is modeled as an ADS with quintessence, so quasi de Sitter and asymptotically into de Sitter, then could we apply this CFT to describe our universe like that?
Well, there is no holography known for de Sitter, which is unitary. I mean, there have been proposals for de Sitter holography more in the context of non-unitary theories, but we have only ADS holography, which is well understood.
But I mean, if it's asymptotical ADS, but with quintessence, could we use holography?
Well, people have tried to understand inflation from holography, but I don't think that has been successful. So people have tried to get to positive potential from viewpoint of holography, from the holography with negative energy, but I don't think there's been much success in there.
Okay, thank you.
And I think that there is yet one other raised hand. Zurab, please.
About the neutrino mass, which you link to the cosmological term with the charge. So, of course, you could, for the case of neutrino, had to discuss some non-abelian charges, presumably. But you mean that they cannot be chiral symmetries? They cannot be singlet particles with massless fermions in that sense?
Sorry, so I didn't claim that we explained the neutrino mass precisely because that the argument that there is in the literature is about the U1 charges, not non-abelian ones. But it smelled like there might be extensions that people haven't thought about yet, but I don't know. So I don't claim that we understood the neutrino mass bound. It was tantalizing, that's all I mentioned. What was your second question? I didn't understand the second part of your question.
No, that was about the existence of chiral symmetry, because you could have zero charge particles.
Yes, so let me say what these conjectures show. These conjectures show that if in our universe you had an suppose somebody says, I have a standard model, SU3 times SU times U1, but sorry, the potential of the Higgs is positive. This conjecture rules it out because you have a chiral massless charge spectrum, and that's a problem. So precisely the fact that in our universe, SU2 is Higgs and the U1 is a necessary prediction of this weak gravity conjecture. So in other words, weak gravity conjecture predicts that in our universe, the SU2 should have been Higgs.
I think that there is also another question from Domenico.
Yeah, at the beginning you said that there is, if I understood correctly, you said that there is a finite number of theories that are consistent with all the requirements. So is this a statement that can be made precise, or
But the statement can be made precise. The statement cannot be proven. So first of all, let me explain first of all what I mean by finiteness. So in the supersymmetric theories, you occasionally have a marginalized space of fields. So when I say finite, I mean within a given expectation value of field change. So that's what it means to be finite, means up to variation of scalar field moduli, which could be infinitely possible waves. So that's a kind of an infinity we are familiar with. We wouldn't call them infinite different theories. We just say they are the different vacua in the same theory. So in that sense, all the evidences we have in string theory suggest there are only a finite number of them. We don't have a proof, but that's the evidence is pointing in that direction. And when I say there are very few, I don't mean very few in the sense of absolute numbers, because they could be, 10 to the gazillions, but still finite. Compared to infinity, it's nothing, so to speak.
No, okay, but I was wondering if that helps you with naturalness. I mean,
not necessarily. It won't explain that, but one could be hopeful that some features of our universe, like I was giving an example, like mass of the electron, some features can be explained without going to actually which one of the universes we live in detail.
Okay.
I also see that Matt Strassler is unmuted. I wonder whether he wants to ask a question or comment, or is just.
It's related to previous questions.
Right,
so.
Well, are there any other questions or comments, perhaps? So if not, I think this is a good point to thank again the speaker for the very nice talk. Oh, sorry.
No.
Oh, that was a clapping hand. Sorry, yes, indeed. So people are clapping virtually, and rightly so. So thank you very
everybody.
much for the very nice talk and for answering the questions. And maybe if we